Okay, let us continue the discussion from the previous part. So suppose you have a matrix A that is n cross n. Suppose you have a matrix A that is n cross n. Okay, and you're constructing x transpose AX, where x is the n cross 1 vector of variables. Then we can actually see, just by doing matrix multiplication, just by applying the usual definitions of matrix multiplication, we'll see that this expression will actually be a quadratic form. It will have the square terms and the cross terms. The square terms will essentially be squares, xi square, and the coefficient of xi square will be aii. Okay, I request all of you to take a few examples and check. This is just basic algebra. Okay, and the cross terms will be essentially terms of the form xij, where I is not equal to j, and the coefficient of xij is going to be aij plus aji. Okay, so here ij go from 1 to n, and of course I have to write I not equal to j because we're only dealing with the cross terms. Okay, so what's interesting here to note is that the coefficients of the square term are essentially ai, which are the diagonal elements of the matrix. Okay, these are the diagonal elements of the matrix, right? And these are the off diagonal elements, or the off diagonal elements. Okay, so the coefficients of the cross terms will come from the off diagonal elements. So multiplication of xi xj will come from aij plus aji, and the coefficient of xi square will simply be ai. Okay, so now suppose I'm trying to do the reverse. For example, given a quadratic form, suppose I'm trying to find the corresponding matrix, then it's very clear. So for example, I have a quadratic form like this, plus 5x1 x2 minus x2 square, right? It's very clear that whatever matrix I construct, the diagonal entries must actually be 1 and minus 1. Okay, because the diagonal entries correspond to the coefficients of the square terms, and the coefficients of the square term here is 1 and here is minus 1, so they have to be 1 and minus 1, right? Now you have some flexibility in the cross term here. So this is the a12, so this is a11, this is a12, this is a21, and this is a22. Okay, a12 plus a21, a12 plus a21 must actually be equal to the coefficient of x12, which is 5, right? So the terms here can just be a and 5 minus a. Okay, this is basically why I wrote what I wrote earlier. Okay, so in general, this is how you would construct the matrix corresponding to a quadratic form. Okay, it's very simple. You just have to read off the coefficients of the square terms and the cross terms, and accordingly construct the matrix. Now, if I the important thing to emphasize here is, if I want this matrix to be symmetric, then there is exactly one choice of the matrix that I can make. Okay, so if I want this matrix to be symmetric, then I want A to be equal to 5 minus A, and I am forced to pick A to be 2.5. Okay, so that follows from essentially the construction here. If I want the matrix to be symmetric, then aij must be equal to aji, and therefore this term here is going to be just 2 times aij. Okay, so if I know the coefficient of xij, I know aij. Okay, so what I want to emphasize is that there is a unique symmetric matrix corresponding to a quadratic form. Okay, there is a unique symmetric matrix corresponding to a quadratic form. This is actually also very easy to see if you just look at, x transpose ax over here. Okay, let us say for some reason that I ended up picking an A that is not symmetric. I ended up picking an A that is not really symmetric at all. Then what I can simply do is, I can realize first that this is equal to x transpose A transpose x. Okay, can you all please think why this must actually be true? I'm saying that x transpose Ax must be the same as x transpose A transpose x. That's very obvious from this expansion here. Okay, because when you take A transpose in place of A, the diagonal entries will not change, and all that will happen is that these two will get swapped. Okay, and that will not really change the sum anyway, so the overall quadratic form will remain the same. Okay, but you can also very easily see it just by realizing that this is actually a 1 cross 1 matrix. Okay, so taking a transpose will not change it. Every 1 cross 1 matrix is symmetric. By definition, every 1 cross 1 matrix is symmetric. Means that X transpose AX is actually equal to its own transpose, and that will precisely give you, when you expand the transpose, take this transpose inside, you will precisely get this expression over here, X transpose A transpose X. Okay, so what does that mean, right? It means that X transpose AX might as well be written as X transpose A plus A transpose by 2 times X. Okay, because X transpose AX is equal to X transpose A transpose X. In particular, it's also equal to their average, right? And then two numbers are equal, the numbers are both equal to their average, right? So that's what I wrote here. X transpose AX is equal to this. Now this matrix here happens to be symmetric, regardless of what A you start out with, right? So even if you started out with an A that's potentially not symmetric, you can always write the quadratic form in terms of a symmetric matrix just by taking A plus A transpose by 2 times X. Okay, so that's basically what I'm trying to say. So the main thing to the highlight is basically this: given any quadratic form, you can write a quadratic form as X transpose AX, where A is symmetric. Okay, and the other way people usually write it is, whenever they see a quadratic form like this, X transpose AX, they'll assume, without loss of generality, WLOG is a shorthand for without loss of generality, that A is symmetric. Okay, you can assume without any loss of generality that A is symmetric. This is what we are going to do from here, right? Whenever we are going to talk about quadratic forms, we are going to assume an associated symmetric matrix. Okay, at this point I can actually ask you a very quick sort of a question. Suppose A is skew symmetric. If A is skew symmetric, okay, so just to recall, what is the definition of skew symmetric? We say a matrix is skew symmetric if A transpose is equal to minus A. Okay, there's some spelling mistake here, it's fine. So if A is skew symmetric, then A transpose equal to minus A. That's the definition of skew symmetric. Okay, if A is a skew symmetric, then what happens to the quadratic form X transpose AX? And what can you say about the quadratic form, right? You can actually use this equation over here, to say that if A is skew symmetric, then its quadratic form has to be 0. Okay, then the quadratic form simply X transpose AX, that expression evaluates to 0. Okay, good. So now, having made that connection to symmetric matrices, and as I told you, why we would like to have symmetric matrices is because we can invoke the spectral theorem, right? And spectral theorem does have huge implications for quadratic forms indeed. Okay, so very quickly, all of you know what the spectral theorem is. Just a quick recollection: any symmetric matrix A can be written as Q times lambda times Q transpose, okay, where Q is an orthogonal matrix. An orthogonal matrix essentially corresponds to rotations or reflections and things like that, and lambda is a diagonal matrix. The diagonal entries of lambda are called the eigenvalues, and the columns of Q are called the eigenvectors of the matrix. Essentially, the idea is that if you look at your matrix A interpret your matrix A as a system that takes an input X and gives an output AX, what you're trying to say is the matrix A essentially acts as a composition of three systems: Q transpose, lambda, and Q. Okay, so this is essentially a rotation or a reflection, and this is essentially a reverse rotation. Okay, all this we discussed in the very first segment itself, and lambda is just a scaling factor, right? It's a scaling of each coordinate. Right? So any symmetric matrix essentially acts like a diagonal matrix in a rotated coordinate space. This is what we discussed in the earlier lectures. Okay, so that's the essence of the spectral decomposition theorem. So now let us actually try to apply that for quadratic form. So suppose you have a quadratic form that's written as x transpose ax, where A is a symmetric matrix. Now I can write it as x transpose times q times lambda times q transpose x, right? What I'm going to do is I'll just make a change of variable. Let me call this q transpose x as y. So I'm going to define y as q transpose x, okay, is essentially the new coordinates obtained after rotation, right? After the vector x goes through rotation of q transpose, the new coordinates obtained are y, and this just becomes y lambda, okay, and x transpose q is essentially y transpose. By the rules of transpose, how transpose applies to a product, it's just going to be y transpose lambda y, okay. Now we see what's happening here. Lambda is just a diagonal matrix, so let's actually write this out and see what happens. y1 by 2 to yn, and this lambda is just a diagonal matrix of lambda 1 lambda 2 up to lambda n, and then there is a column vector of y1 y2 up to yn, okay. So as you can see that you have a diagonal matrix here, there are no off diagonal entries, right? So when you expand this, you are not going to get any cross terms, you are only going to get the square terms, right? So this is just going to be a summation of lambda I yi square, I equal to 1 to n, okay. So you see what has happened here. You had a quadratic form that potentially had both the square terms and the cross terms to begin with, right? So you might have had a quadratic form like x1 square plus x1 x2 plus x2 square to begin with, which has both the square terms and the cross terms. But here, after doing this change of variable, so to speak, what you end up getting is only the square terms. There are no cross terms here, right? Of course, each of these yi is some linear combination of xi's, because y is given by q transpose x. So each coordinate of y, that is y1 y2 y3, are in some sense some linear combinations of the x's. It's some combinations. So that's basically what's happening here. So what you're saying is that every quadratic form can be written essentially only using the square terms, by completely avoiding the cross terms, okay. And there are huge advantages to this, because first of all, such an expression is much easier to understand. We'll look at the geometry of such expressions in the next portion of this lecture, okay. Such expressions are much easier to understand. I do want to emphasize here that these quotients lambda I can potentially be negative or 0 or positive, right? So it's not to say that this is just a sum of squares. It could actually be a sum or a difference of squares, and some squares could be missing altogether, right? That's fine, right? For example, we can write, let's take a very simple quadratic form x1 x2, right? This is a quadratic form, correct? I mean, you can actually write the corresponding matrix as x transpose times 0 half half 0 x, right? So this is a quadratic form. You can as an exercise, you can find out the eigenvalue decomposition of this matrix and try to construct the summation of lambda yi square, but we already know what it must be, right? So it's actually equal to x1 plus x2 whole square minus x1 minus x2 whole square by 4, okay. So it's 1 by 4 minus 1 by 4, right? If you actually expand this, you'll actually get x1 x2, correct? So by taking the eigenvalue decomposition of this matrix, you'll actually arrive at the same conclusion, right? You will actually get the same conclusion as this, right? The point I'm trying to make is that this is obviously a very simple scenario when you just have two variables and only one expression x1 x2, but even in general, when you have many variables, you can always do this, right? You can always combine the terms in such a way that you actually only end up getting sum or difference of squares, okay. So that's the direct application of the spectral decomposition theorem to quadratic forms, okay. We'll stop at this point. In the next portion, we'll look at the geometric interpretation of quadratic forms.